We'll get started here. Today is the second lecture on these spatial spatial statistics, spatial inferential statistics, and it's on area pattern analysis. And then the last subject that we really need to talk about is correlation. We'll do that next week. So the final for this class, I don't know if I've explained this, but maybe feels like deja vu when I thought about it in my head. But because this was originally a night class, the final is supposed to take place on the last day of class.
Oh yeah, we did.
Okay, so that would be May 3rd or whatever, or 2nd, whatever the. Let me see, whatever the day that is. It's May 3rd. Yep, so I was right at first. So the final is going to be May 3rd, and I won't be here. Yeah. So I'm trying to decide whether we should just do, because we've got Maggie down there, and there's only 4 of you up here, or we should just do kind of like a take-home assignment instead of the final, because I won't even be here. I'll be traveling. So that'll probably be what happens. So although it's May 3rd, that'll probably just be, and in fact, since that's early, we could just not meet May 3rd, and I could come up with a different due date. So that's probably what will happen.
I think we have other presentations that week.
Yeah, that sounds good. Yep, I'll decide that this week and report back next week. Exactly the format of the final, but in the small chance that I get a proctor and it's in class, then it will be the same time, 9:30 during class, because it was a night class and that's the official time of the final. Okay, so good question. All right, so today we're going to talk about area pattern analysis, and there are basically there's 2 area pattern analyses that are talked about in the book, and we'll go over those. And then also there's another quite popular area pattern analysis that's used fairly often. Well, there's a family of these tools that were created by another scientist named Arthur Geddes. And so we'll talk about those too, even though they're not talked about in the book. But actually, we're not going to spend a lot of time other than kind of like the basic how the math is done for the last 2 ones that are pretty computationally intensive. We're not even going to really talk about the math. We'll just talk about why it works. Kind of a departure from the earlier topics. Okay, so the goal here is similar to point pattern analysis, but it's going to be looking at area patterns instead of point patterns. And I think we had a picture on the slideshow last week that talked about the difference here. So one of the things that we can do with areas that we can't do with points is look at their common borders and use their common borders as indications of a neighborhood. Remember last week we talked about what is a neighborhood. And so we could say in a situation where we had things that were next to each other sharing a common border, we could think of that as a cluster. And things that are next to each other that share a common border that aren't alike, we could think of that as either random or dispersed, depending on the exact pattern. So we still have that continuum that goes from random to dispersed. From random to clustered, dispersed to clustered with random in between. So dispersed means that there's a pattern to the distribution. Clustered means that there is a pattern too, but it's things that are nearby have the same value. A checkerboard pattern would be very close to, or would be a dispersed pattern. A random means that the the arrangement is purely random. There's not really a rhyme or reason to it. So if we think about a chloropleth map, hopefully we know what that is, but like it's a map where all the units are colored a certain color representing how much stuff they have, what's being mapped. So they're clustered if adjacent or nearby areas have similar values or scores, but they're dispersed if the values adjacent and nearby tend to be dissimilar. And then they're random if there's an even mix of sometimes there's dissimilar values and sometimes there's similar values. All right. So that's how that continuum works. So the type of analysis that we're going to talk about that quantifies this, that basically says, oh, you have a clustered region or you have a dispersed region. The variable you're looking at is clustered or it's dispersed. It's used for many geographic problems, especially temporal change. You can basically come up with a number, and I know I talked about this a little bit last week, but you can basically come up with a number that says this phenomenon, this variable, is getting more clustered over time. So you could look at an immigrant city and see if in that city certain patterns of ethnicity or background have become more clustered over time or less clustered over time. So you could have a hypothesis that the ethnic makeup of the city is turning into a melting pot, or is it turning more into a vegetable salad where people are clustered? I don't know if that's an analogy. Hey, yeah. All right, so here's a chloropleth map where we've got land deforestation. And looking at just this region here, we could run an analysis to see if the land that was being deforested was clustered over time. So this is not a socioeconomic, but more of a land use environmental application. So over time, we could look at the areas that were being deforested, and we could answer the question, is it becoming more clustered or less clustered? More dispersed or less dispersed over a time period? Most likely, in that case, it's going to be fairly clustered, but we could see, if maybe maybe the people that were doing the deforestation implemented a new policy that was trying to make it less clustered, like they were trying to take from various areas to, minimize the impact. And they wanted to see if that was in fact working. They want to come up with a number. How less clustered is it getting? Or how, yeah. Then they could run these analyses that we're going to talk about today. So the first one is rather basic. It's the easiest to calculate, probably the easiest to conceptualize, is this joint count analysis. Okay? So with joint count analysis, we're really just looking at the boundaries and whether or not a join is just a boundary. So each boundary here is a join. Whether or not that join has because the join represents two polygons meeting, whether or not those two polygons have the same value or different values. So a join has an attribute of having two neighboring polygons. And those two neighboring polygons both have an attribute. So, when we use the word join here, it's not the exact same as a table join. This is a common boundary. Two areas sharing a common edge or boundary. So we can count the number of joins. The number of joins is just the number of common boundaries. So by definition, this right here, I'll point that out on here for Maggie later if she's watching the video. Right here, that common boundary wouldn't be considered a join. But all these other ones, the ones with little lines on them, are joins. So this first statistic is binary. It only works with ones and zeros. And so you do have to collapse your data into that format in order for it to work. So we're looking at, an example here would be a candidate either won or lost an election in a particular polygon. So, in the United States, it would be, did it go Democrat or Republican? That's fine. You could use joint count analysis on that sort of data. And you would probably find almost certainly that that variable was clustered. People nearby tend to vote more similar. But it might be interesting in different places that it might be less clustered, more clustered than it was in other places. So you got the data down to a very fine level, county or below, you could check that. So here's just another diagram for the United States showing, I don't know which election this was, but Minnesota voted differently than any of its western neighbors, South Dakota, North Dakota, but both Nebraska and Kansas voted the same. So you come up with what's called a contiguity matrix. So for every single join, you have the left and the right polygon value. All right. So this would be an example of a contiguity matrix. So you have the number of joins, and in the book, these are always referred to as either white-white joins, black-black joins, or white-black joins. In other words, another way to say that would be, you've got two values, so you've got both polygons have the same value, and there's one of the values, or both polygons have the same value, and they're the other value. That's the black-black and the white-white joins. Or they've got a mix. They've got one of each, and that's what's referred to as a black-white join. So you get this contiguity matrix, and you can calculate the value for the joint count analysis. So the goal of joint count analysis is to find out if the distribution was generated by a random process, or if it's not clustered, or if there's a pattern to it. So it'll have negative values if it's distributed, and positive values if it's clustered. So there we go. Oops. Now there are two different things to consider, I guess. Well, there's one thing to consider, and that is whether or not the joint count analysis is what we call free sampling or non-free sampling. Basically, this boils down to what it says there. If a researcher can determine the probability of an area being either black or white on a theoretical idea, or by referring to a larger study. So you would use free sampling in those cases where you knew that there were, let's say, 10% in one category and 90% in another category. You knew that's the way it should be. You had a predetermined knowledge of the proportion of both of both categories. Or if you wanted to compare and say this smaller area should have the same distribution as this larger area, that's when you would use free sampling. Okay. So the big example there, you want to analyze one portion of a metro area to compare with larger or entire area to see if the overall probability holds. That's when you use free sampling. Non-free sampling, probably slightly more common, but maybe not much. But that's kind of the default, I would say. So you've got, in using non-free sampling, you've got you're just studying it. You've got no reference to a larger area, then you use the general theory. So, in the example we gave with the United States elections, for any given election, you don't have any assumption as to what proportion of people should vote a certain way, and so you would just use the non-free sampling technique. And the math is slightly different for each. The book actually doesn't go over the math for the free sampling technique. So this is the free sampling technique formula. Your book doesn't use this, and so all the examples are from the non-free side. The math is actually a little bit simpler for the non-free normality sampling. But in both cases, this is the test statistic. It's kind of familiar. You've got an observed and an expected value, and you subtract the observed from the expected, and you divide that by the standard error of the expected. And you could use any one of these lines. So in other words, you could use this line. So this would be if you wanted to calculate the just for the black values, the white values, or the black white values. Most people use this one line right here. So basically, what we're doing here is looking at the black white pairs. And in the free sampling technique, you do need to have that expected proportion of black and the expected proportion of white. That's not necessary for the non-free sampling technique. But if you're doing the free sampling technique, you feed it the expected proportion for black, the expected proportion for white. You could call them category 1, category 2. And then you multiply that by 2 times k. K is the number of regions. And then you get a number. You do the same thing over there. You do have to use this formula to get that value of n. But once you do that, you can feed that into the formula, because this will give you the denominator, and this will give you part of the numerator. This will give you the expected, and then you count up the observed. The observed is what you actually see. All right. So for non-free sampling, really I don't know if I should write non-free sampling there, but this is the hypothesis test. It's really the same for both, non-free or free, but the math on the next page is going to be the non-free sampling math. So in this case where we're using join count analysis, we need to find the observed number of black and white joins is equal to the expected number of black and white joins. That means that there's a purely random pattern. So that's the null hypothesis, that there's a purely random pattern. And there can be a two-tailed or a one-tailed test to this. The one-tailed would be that it's more clustered or more dispersed. The two-tailed would be that the pattern is just non-random. We don't care whether it's clustered or dispersed. Not that we don't care, but so you could look at it and say, oh, that definitely looks clustered, and so we test it to see if it was clustered, and in that case we could do a one-tailed analysis.
Can you just like the difference again between the non-free and free?
Sure. So the main difference is that you have an expectation of the proportion of the two categories. Like you're testing to see not only is the pattern clustered or dispersed, but if it definitely is like an 80-20 split. So like if you know that there should be 80% in one category and 20% in the other category. If you know that by default before going into it. So it's less common, but like let's say I did a one of the most common applications would be what they said. So I've got, for the whole United States, I've got some category I come up with. We've got yes or no Republican or Democrat or something for the whole United States. I've got all the counties in all the United States, and if I come out with a, there's 60% of one category and 40% of another, and then if I wanted to test a smaller region and say I believe that this smaller region should have the same proportion, then I'd use the free sampling technique rather than the non-free sampling technique. Then maybe in like a land cover analysis, yeah, in a land cover analysis, I guess you could use non-free sampling if you actually knew if it's a wall-to-wall study and you actually know that it's 60% urban and 40% agriculture, then you could use the non-free. I don't see why you couldn't use the non-free. I mean, you're trying to decide whether or not it was clustered or dispersed. Then you could use the non-free sampling technique. I mean, the free sampling technique. If you know the proportion, use the free. Yeah. Yes. Yeah. Or you don't know it, or you don't, or you just assume that it doesn't. Yeah, that it's.
Like when you have no expectation.
Yeah, when you have no expectation of what it's going to be, that's when you use a non-free. Yep. So the test statistic is the same, non-free. This is just a slightly different way to word the math, but still observed, expected, and divided by the standard error of the expected, or yeah, standard error of the expected. So this is calculating your expected value. This is this term right here, your expected join count. In other words, how many times there should be, if it was random, how many times there should be a black and white join. In other words, a black next to a white value. So this is how the OBW is how many times there actually was a black and a white next to each other. The EBW is how many times there should be a black and a white next to each other if it was random. And this is the formula for that. Okay, I didn't put all the text there, but it's in your book. But basically, this is 2 times the number of joins, the number of black joins, the number of white joins. You multiply all those numbers together, and you divide that by the total number times the total number minus 1. All right, and we'll actually we can actually practice doing this. So you can automate this into GIS, although there isn't a tool by default in ArcGIS. I'm sure you can write one or make one in Model Builder pretty easily. But this would be, if you were going to do it, this would be the reason you couldn't do it, because that's a large formula. So we've got a bunch of numbers, and this tells us what they all mean, but calculating them could be a little bit tricky. So we've got the these are all pretty self-explanatory. The number of black areas, the number of white areas, the total number of areas, the total number of joins is just the total number of relationships between lines, and the sum of L is the total number of links, which is 2 times the number of joins. So a link is technically the relationship between each polygon. And so a link happens twice, and that's why it's 2 times the number of joins. So if we have all the counties in Mississippi, we can think about how Forest is different from Lamar County, because they're next to each other, and then also how Lamar County is different from Forest County. So those would both be links. So a join is the common boundary, and a link is the bridge across the common boundary. So there's only one common boundary between Forest and Lamar, but there are two links. There's a link going one way and a link going the other way. Okay. So that's what L is. So L up here, the sum of L, L minus 1. So there's a bunch of links. This math is probably going to make more sense if we actually do it. So I was thinking we could do that. Might take a few minutes in ArcGIS to do. So this is your homework one. I uploaded this. It's there. I think what I'm going to do for this, though, rather than do your homework right here in class, is to just redo this real quick. Not redo it. We'll come back to this. So I believe I uploaded the data before, but if I haven't, you can just follow along here. That's not what I meant to do. I meant to get the counties. All right, so we've got our counties, and I think the first thing that I'm going to do is to select state name equals, let's just do Mississippi since that's where we are. Mississippi. And we've got a lot of a lot of counties. Probably too many counties. I don't know if that's possible. One thing I'm going to do is change the coordinate system to Mississippi. And you don't really have to do this for joint count. Analysis because we're just looking at common boundaries and we don't really care. There's no measurement of distance, or there's no measurement of boundary length or anything like that for this. We're only concerned about joint count. Okay, so I am going to go ahead and export Mississippi out as a separate unit. Yeah, I'll put it right there. Call that LS. Selected features, the data frame. Okay, yes. I'm going to start over. And just reload. All right, so calculating these values out. If you look at the work table in your book, there is a table 15.3. So the first thing that we need to do is come up with the total number of links per unit. So we've got counties, right? We've got counties here, and we need to come up with the total number of links per county. Now, we have polygons, and we're trying to get attributes of these polygons that have to do with the polygon next to it. In the old days, there was this thing called a coverage, an ArcInfo coverage, and you can actually use a coverage to find out the common boundaries that were around it. Shapefiles and geodatabases don't store that information. In other words, this common boundary right here is actually in the computer system twice in a shapefile. It's not stored as just that boundary. This county, whatever county that is, I don't know what it is, but it's stored as a polygon that goes all the way around like that. In other words, this line isn't any different than this line, than this line right here. Those are the same lines. And there's another line that does that hole. So that boundary is repeated, which is actually kind of good for our join count analysis, is that line there is stored twice, stored in the system twice. And we need it to be because a link represents the jump across the boundary, not the boundary itself. So we need both directions, I guess you could say. All right. It's a little convoluted as to how to extract that value out of a GIS, but it's actually not that difficult. Okay. So I'm going to show you how to do that. The first step is to actually convert all of these polygons into lines. So there's a tool for that. That's in data management, and it's under features, I think. Yeah, I'm just going to have to search for it. Geoprocessing, search. Whoops. Search for tools. Oh, actually, before we get any further, I got ahead of myself. This data doesn't contain anything that has a yes/no category to it. It's all got continuous data, and it's kind of old data, but we've got all sorts of information, and we need to come up with a yes/no category. Anybody have any ideas of something they want to test? Maybe, let's just look here real quick. So, maybe something that might be not, or that would be less clustered, because most of the racial and ethnic categories are going to be pretty, I think, pretty clustered. Let's total population. So that looks pretty clustered, although, I mean, it'd be interesting to test, I think. Hispanic. Yeah, that might be pretty interesting to test. That doesn't look like there's a lot of clusters at all. And then I was wondering if one of these, males or females, wouldn't be very clustered, probably, because people tend to not cluster based on gender too much. So anyway, but maybe Hispanic. That might be something that people are actually studying. The demographic change associated with that. And so if we divide that into two categories, let's see if it's more clustered. Oops. And I'm gonna say two categories of quantile. That way they'll have exactly the same number in each class. All right. So we're going to see if that pattern is considered clustered or not clustered. It doesn't look. It does kind of look clustered in that there's some clusters, but these clusters are so long and thin that when we do join counts, we might get some value. So you can ask a legitimate question: are those clustered or are they not clustered? Because it kind of looks like the I-59 corridor. Which one's high? I guess this one is high. The reason why I'm normalizing by population is because we wouldn't just want to use a non-normalized value, because if we did, basically Hispanics would live where people live. That wouldn't be a good question to answer. All right. So if I take this number right here, what's that number? 0.1. So I should have actually prepared and had this category already in there, but I didn't think about that. So I'm going to add a field, and I'm going to call this. I'm just going to make it text and say HH, or just H. I just need to make that 10. Okay. Doesn't need to be a big field. So then I'm going to do a field calculator, and I'm going to do something like actually, I'll do this in 2 steps because it'll be faster. Field name. So this first field is going to be, what I'm going to do is divide the Hispanic population divided by the total population, and that will give me the ratio. And then you know what I could do? I've only got 82 counties, right? So it might just be faster to sort them and select 41 counties. 41 counties selected. So now I can just say low for the lower values. Field calculator. It's double quotes. Field calculator. Python lets you use single quotes or double quotes. I got confused there. All right, low, and then I'll switch the selection. This little guy, and then I'll say field calculator and high. So I've got those counties with a higher Hispanic population and those counties with a lower Hispanic population. All right. So now that I have that, I'm going to remove the selection. Now that I have that, I can go ahead and prepare my joint count analysis. So the first thing that I have to do is turn those polygons into lines. Now, what it's going to do is create a ring for every county. So this is the one where I could say feature class to line is the tool that I want. So what it does is just convert, and then maybe it's just called feature to line. Yeah, feature to line. So what it does is it just converts every feature into a line. And I do want to check preserve attributes. So I leave that checked and I say OK. And what it does is it goes through and creates a line shapefile from my polygon shapefile. So turn it off, it looks like that. My line shapefile. And the next thing that I want to do is, and this is the part that you may think, why does that work? I don't know why it works, but it works. If we intersect this line shapefile with itself, in other words, you can intersect two. You know what an intersect does? Maybe you don't, but an intersect basically takes 2 data layers, and anything that's common between the 2 data layers, it creates a new line in the output table. And so when you intersect it with itself, anywhere that this line that's going all the way around this county intersects with this line that's going all the way around this county, it creates a new line just that their common boundary exists. And so it creates a new line right there. It'll create a new line right there. Everywhere where there's a common boundary between 2, it creates a new line in the output data set. Actually, before I do that, in order to make our data set not just have a ton of data, I'm going to drop all the fields out except for the ones we care about. So there's a tool called delete field. So I'm going to delete out of our feature to line I'm gonna delete everything. I'm gonna delete everything. The third time. Except I want to keep the object ID. I want to keep the name of the county. We all know that they're all in Mississippi, so I don't need to keep that. I only need one of these. I don't know which one's more important. I'll keep the object ID, and then I want to keep the data set, the H that the high-low for the Hispanics that we calculated for the Hispanic population. Okay, so I'm keeping object ID, so I have a unique ID reference, and keeping name, and I'm going to say okay. Then I'm going to open the table up to make sure that it looks good once this finishes. So yeah, I think this will be fine. This object ID refers to these are basically the same, okay? But this refers to the county name. We're probably just going to be able to work with the county name, but I kept this in just in case. And then we've got the high and the low down here. These are the two fields that we really care about. Okay, so now on to the intersect. This is where the magic happens. It lets us do the join count analysis. Is this intersect? All right. Intersect. So you feed it the line twice. And we'll see in a second. One thing that I really recommend when you're doing join count analysis or actually intersecting lines ever is that you do set this XY tolerance. If you don't, the default is 0. So when whoever made this data set, if the line is not exactly the same, the line that represents Lamar County and the line that represents Forest County, if they're not the exact same line, then you're not going to get that new line. Okay? You're not going to get that common boundary line. So if you set an XY tolerance, it will go out beyond that. And if the lines are within that distance, it'll say, okay, those are the same line. So for this type of analysis where the actual area doesn't even really matter, the area, things like that, the distances, I select a fairly large thing. I'm going to go 1,000. So in other words, if a line is within 1,000, that might be too big because of some of these things that come back in onto each other. Oh, it's compromised. I'm going to go 500. So I'm going to select 500 meters. And so if a line is within 500 meters of another line, it's going to be thought of as the same line. Say OK. And that'll run. I'm not really paying attention to where I'm saving these things, which is fine. All right, so now I'm going to turn off this other one, and I have just this one up. This is the result of the intersection. I'm going to select, let's go back, I keep pointing to this one, but let's go back to the Forest County, Lamar County boundary right here. If I select just the boundary there, see how I selected it? And it's its own thing. Let me turn this off and turn this back on. And if I select that boundary in the other one, feature to line, oh, well, anyway, it worked. So if I open this up, now, I thought I selected that line, or did I select off of it? Okay. So I select on that boundary, that's the entire boundary. If I go back into here, there are 4 features that are selected in this boundary. Do you see that? There are 4 lines. These are the 4 lines. Okay? And we can, if we read these lines, we can see what they are. Okay? One is the forest to forest line, because we intersected 2 layers. And so one line was just the 2 forest boundaries hitting each other. This next line is where Forest County hit Lamar County. Forest County from one layer hit Lamar County in the other. This one's where Lamar hit Forest in the other. And this one's where Lamar hit Lamar County. Now, two of those we care about, and two of them we don't. Okay? We don't care about the common ones, Forest to Forest and Lamar to Lamar. Those are not necessary to calculate the joint count analysis. However, both of these are. These are both considered, Forest to Lamar and Forest and Lamar to Forest are both considered links, not joins, but links. There's only one join there, but there's two links. These are both considered links, and we need to save the information about them. We need to have that information in order to get our links. So, the first step, or the next step, we need to do is to just select. We need to take out all those what do you call them? Those links that we don't care about. Okay. So if we select, first I'm going to clear selected features, because if you operate on selected features, it doesn't work. Selection. Oh, I did clear the selected features. Okay. So I'm going to take my intersect, and I'm going to make a new expression that says if the, and I know now these fields are really hard to really know what is what, but we've only got two fields called name. So if I say name does not equal name, oops, I'm going to select all the places where the names aren't equal choosers. So I'm going to eliminate all those Forest to Forest and Lamar to Lamar and all the other counties in Mississippi. So I need to do that. Okay, so here's my, I'm going to call this select instead of the, whoa. Yep. Okay. So I hit OK. And once that's run, now if I compare the two attribute tables, this one has 836, and this should have about as many fewer as there are, double the amount as many fewer as there are counties, but even a little bit less, because now we're actually also getting rid of all of, you see how we got rid of all of the things that aren't even links at all, the exterior boundaries, we got rid of all those. So it has a lot less. It has 400 left. So we're left with 400 links. So that's the number of links that we have in our data set. So we've got 400, and we need to come up with a table that looks kind of like table 15.3 in order to actually run this analysis, where it has the number of links, and then it has L minus 1 and L times L minus 1. So for each county, we need to find out how many links each county has. Is basically what we need to do to create this table, because that's part of the math. All right. Yeah.
I see the expression you used.
Oh, yeah. Oh, well. Select. Oh, it disappeared, but I can get it. Customer processing results. It's just name does not equal name 1. So it automatically names the new, because there's two fields. We use an intersect. So one of them gets named name, and the next one gets named some auto-generated, usually name underscore 1. Does that work? Is that good? What's that? Did you click this little button and just actually choose the fields? both have to. Or are you doing with Connecticut right now? Now with an area that big, it's easier to just do that. If the SQL statement. Name. And then is there a name one? Yep, name one. Well, it's down saying this isn't that.
Oh, that's because it's on. But it's an empty, it was an empty out.
Well, is this an empty output or does this have the right values?
This is the right one.
Oh, is anything selected? Even in the Connecticut counties? No. So what does the line intersect look like? I'll go back. Go like this. Which one's select by attributes? Say name is not equal. Go down. And then just export that because that'll have the same effect. You know what I'm saying? So we just did it a different way. I don't know why it didn't work. I probably figured out if you experimented with it for a few minutes, but. Maybe it's because you need the quotes around name and name one. Because it's a shapefile. You tried it? Okay.
Yeah.
All right. So we've got that. We're all set. So now we have this. The shapefile. We have the 400. So we need a way to collapse this down into. We need a way to collapse this down to find out how many links there are per county in order to make table 15.3. That's not the only thing we do, but we do need table 15.3. So what we need to do to make table 15.3 is what we call a dissolve, or if we don't really care about the the geometry, which we don't, we can simply do a summary statistics. So summary statistics is the same thing as a dissolve, but it ignores the geometry. It just creates a table. So what we want to do is input our table that we just created, the select, and I'm going to save this actually as a DBF so I can import it into Excel. Yeah, so I can import it into Excel. So I'm going to put this in C. I've been working in Connecticut, so I'll put it back there, even though we're working on Mississippi now. Connecticut, and I'm going to save this table as a link table. Actually, I'll call it sum link table .dbf. I'm going to save it right there. And then the statistics field that I want to summarize actually also doesn't really matter. Okay, we're collapsing everything, and so. We're collapsing everything based on a case field, so the case field does matter. We need to, it doesn't matter whether we do name here or name one here, but we need to select one or the other. Okay. I just usually select the first name. So what it does is now it's going to collapse everything into name. Okay. All right. And the statistic that we choose, it doesn't matter too much, but you just want the count of how many links there are. So what I like to do is say name one, and then as the statistic, I just choose count. So this is what it's going to do is it's going to create this exact table on 15.3. I'm going to have all of my county names listed, and then the number of links is the count of the other counties that it touches. So that's what we're saying here, is these are the other counties, and this is the count of those other counties. These will be the rows, and this will be the count of all the counties that it touches. So I've got my sum-link table. I hit OK at this point, and it's going to go through, and we'll see if it works. I'm going to open the attribute table, and let's go down to Lamar County. It says that there are 5 nearby counties. Okay, so it touches Forest. We know that. 1, 2, 3, 4, 5. Now, the very corner of Lamar County, no, it doesn't. Never mind. There's not a 4 corner, so there's not an attribute there. Sometimes, I don't know what county this is, but we should check it out. Sometimes in ArcGIS it'll count it, and sometimes it won't. Do you know what county that is? Okay. Because it doesn't always share a common boundary, and that is a drawback of doing this in a GIS. Let's see what county this is. This one right here, Neshoba. All right, so let's see how many county bound neighbors Neshoba got. A, B, C, D. Because technically joint count analysis, you have to share a common polygon boundary. So a point doesn't work. 4. Okay, so it worked. Okay? But sometimes, if that boundary was drawn slightly wrong, then you'll get a join between these two. Okay? And in an analysis this size, it doesn't really matter one miscounted join, because there's so many. It's such a large number that the math isn't going to be too sensitive to a little thing like that. Okay, but I'm glad it worked in our case, at least for that one. There's other 4 corners to check, but okay. So that's our link table. So that's the number of links. And in fact, the reason why I said it doesn't really matter which one you choose, whether you choose, because this column always gets created, and that column always has the information you need. They're the same. All right. So this is L, the number of links. Okay. All right. So I'm going to selection. Clear the selected features. There we go. And we're back to 82 counties. This number should always match the number of the original polygons. Unless, like if we did the United States and we threw Alaska in there by accident somehow, Alaska would have gotten eliminated because it doesn't have any common boundaries. Okay. All right, so what other information do we need in the formula? The only other piece of information that we need, but we don't need it, nothing in the big old standard error denominator needs anything else. We've got all the information we need for the denominator, because this table does the denominator. It has all that information that we need. So let's put that aside for a second. Okay, the number of white, in our case, the number of high Hispanic areas, the number of low Hispanic areas. All those L's are already done. The J is done because it's defined as 2 times. We can just take the number of L's and divide it by 2, and we get that. Okay. The only other thing that we need to create is in the numerator. No, the numerator is fine, but in the numerator, we need to get the observed number of black and white joins. That's the only other value we need to finish the formula off. Because the other half of the numerator, the EBW, is also contained all in this information. We have all the information we need to do EBW. Okay? All right. So OBW is the last thing that we need to do, and that's the observed number of black and white joins. We can get that really easily because we have all the links, right? The links are right here now, and in these links we've removed, in these links, we've removed the common forest to forest link. However, we still have, these are links, not joins. So we still have Hancock and Harrison, and then later we'll have Harrison and Hancock. Harrison, Hancock, Hancock, and Harrison. You see how we have that join twice? We have this join twice. In other words, we have it as a link. So all we need to do when we count up the number of links that are black and white, we need to do what? Divide them by 2 to get the total number of black-white joins. So we can just simply go into here, select by attributes, and say H does not equal H1. What we're saying there is that we're selecting the areas that are black-white joins, right? When they don't equal each other, we hit apply, and now we have all those, the not the same category values. So we've got the high, the low, and anything where one's high and one's low. However, this number, 194, represents the number of links, and we need the number of joins. Okay? What I mean in there is that there's going to be 2 sets. So there's the Harrison Stone and the Stone Harrison. And the formula asks for the number of joins, the expected number of black-white, or the observed number of black-white joins. So our observed number of black-white joins is this number divided by 2, 194 divided by 2. So now I think it's time to start calculating these values out. So I'm going to go ahead and open up the okay, hold on here just a second. Oh, good. I'm going to, now that I have all the data prepared, I'm going to stop the recording because this class